Hello, PreCalc. Today we're going to study Edgenuity Section 10.1. It is called Understanding the Concept of a Limit. This is the first look into actual calculus. Limits is where calculus starts. Excuse me. We have three objectives for this section. Estimate limits from graphs and tables. Find one-sided limits from graphs and tables. Determine if a limit exists at a point, and if so, its value. So let's look at our first problem here. Use the table's over here, to determine a reasonable estimate for the limit of this function here. And let's talk about how you read that. The limit as x goes to 3 of the function quantity 2x squared minus x plus 15, all of that over quantity x cubed minus 5x minus 12. So look at what we do here. Look at how the table is constructed, first of all. We want the limit as x goes to 3. So the way the table is constructed is numbers just barely to the left of 3 if you're thinking on a number line. If I put 3 here, I'm picking numbers just over here if this is like 2.9, and then numbers just over here if I'm looking at like 3.1. I'm picking all these numbers just barely to the left and right of 3. If you actually put 3 in, you'll find that you get a 0 down here. So that's why when we put in 3, we have an undefined value here. So we put all these values into this table, and it gives us all these values, and what we want to do is try and figure out, okay, based on the construction of this table, based on the evidence that we see over here, what sort of value, what sort of f of x value, that is, what sort of y value, are we approaching? And limits are all about approaching values. They're never about getting to values, always about approaching values. So what value are we approaching as the x value comes real close to 3? Okay, so you'll see that here's from the left, we approach a value of 3, and you can see over here we got 0.5116, I'll truncate there, 0.5011, 0.5001, and so you can sort of see evidence that we're approaching something there, and then as we get closer and closer to 3, you see as we start, if you look from the bottom up, we go 3.1 and then to 3.01, so we're getting closer and closer to 3 that way. And over in the y values, we're going from 4.888, 4.988, 0.49988. We just keep getting closer again to 0.5, right? So the estimate, and you can only really estimate things from a table like this. You can't say for sure that that's the limit, but you can get a pretty good idea of the limit. There are ways to exactly calculate the limit. I do want to point that out. But we're not there quite yet, okay? We're just talking about, if you're looking at a table, what's the intuition here? What does it seem to be telling you? And as I approach from the left and as I approach from the right, I appear to be getting closer and closer to 0.5, right, to 1/2. So we're going to estimate that the limit as x goes to 3 of 2x squared minus x plus 15, all of that, over x cubed minus 5x minus 12 approaches is, well, we're estimating, so I'll say equals. It's a little redundant to say that a limit is approximately. A limit is already equal to and approximately almost at the same time. So, but let's just say that our estimate is that this limit equals 0.5. All right, I'll give you a moment to look at that. And let's move on to our next problem. All right, we've got another table, just a different looking table, but I wanted to show it to you because it's a slightly different looking table. We have a function f of x. We don't know what that function is exactly, but we have a function f of x. It has values given in the table, and we want to find the limit as x goes to 2 of this function f of x if it exists. So if I go back for a moment to the previous problem, notice that both from the left and the right, we appeared to be approaching 0.5. That is how a limit does exist. Okay, if you approach it from the left side and the right side together, and you get the same value as you approach, and you sort of keep approaching that value the whole time in the very small values, then you can say that the limit exists and it's this, or it looks like it's this if you're looking at tables. So notice here we've got these three x values starting at 1.99 and approaching 2. These three values starting here at 2.01 and getting closer and closer to 2. So in the theoretical middle here is 2, and they don't bother with it because something weird happens at 2. It's undefined somehow. So instead of putting it, they just put numbers very close to it. So what happens as we approach from the left, okay? As I approach from the left, I've got these weird values. It's 0.505 and then negative 0.827 and then 0.306. That's a little weird. I should be kind of approaching the same number all the time in the same way that I was approaching 0.5 here. So that's a little weird. Same weird thing happens as we approach 2 from the right here. And so we go, if you start from the farthest right and moving in towards 2, we get negative 0.506 and 0.827 and negative 0.306. And so when we're looking real close at 2, when we're looking at this theoretical middle here, it doesn't really make sense that we're approaching anything at all. These numbers seem to bounce around in sort of a random way. So from that, you would guess, now this is not necessarily the case, and I want to point out that this is just extrapolating from the evidence that we have in the moment. But from the evidence we have, from the data that we have to make the mean girls statement, the limit does not exist. Okay, so that's our That's our conclusion to this one. And again, that might not be right. But that's what the table makes it look like. And we have to go with what we see from this table. You might even be more accurate to say it appears that the limit does not exist from the table given. But in general, in this one, it looks like the limit does not exist. All right. Well, let me give you a moment to look at that before we move on to the next problem. All right, let's look at our next problem. Now we're going to talk about graphs and how graphs deal with these ideas, or how we deal with the idea of limits when we're looking at a graph instead. Okay? So we've got a graph plotted, and it certainly appears that this graph is in radians because we've got pi's and pi over 2's and stuff like that. And we've got some function f of x that is graphed. And we want to estimate the limit as x goes to pi over 4 radians, which would be halfway between 0 and pi over 2. So we're going to have to think about that value here. And so we want to make sure of a couple of things. First of all, are we approaching that value the same from both ends, from the left and from the right? So I'm going to make another one. I'm going to make another version of this graph, but I'm going to kind of zoom in. Okay, we're going to put pi over 2 right there. And we're going to put, let's say, -1 there. We'll put -2 down at the bottom here. And what seems to be happening is that we've got this, or maybe better, that goes on it. If I'm just zooming in here, well, somewhere in there actually it starts to turn, right? Kind of right around the end there. So something like that. I don't know, I'm not drawing it very well. But we've got something that, here we go. Something like that. Okay? And what we're interested in is pi over 4 radians, and what would be the y value on this graph for an x value of pi over 4 radians. So all we're going to do is kind of come down here and mark that and say, okay, for that point, the x value is pi over 4, and then we got to ask ourselves several questions. Let me switch colors here so I can sort of draw over this. First of all, for this point, as I approach this point along the graph from the left and from the right, am I approaching the same value? That helps tell me whether the limit exists at all. And certainly appears that way in this one. And second, what does that value appear to be? And of course, I haven't drawn it very well and stuff like that, but it appears to me that it looks like that limit is -1. Both of these methods, looking at tables, looking at graphs, can really fail you because you're only approximating. You can only ever estimate with these. Because you can't like zoom in infinitely close so that you can really see and check what that Y value is. All you can ever do is say, it looks like, it appears to be this, right? So that's what I'm doing here. I'm just saying, well, it looks like that, and that'll have to be close enough, and so it looks like the answer is -1. And that's all I can really say about it. It appears that the limit as x approaches pi/4 is of f of x is 1, or is -1. And that's all I can really say about it. Okay? I'll give you a moment to look at that. And let's move on to the next problem. Now let's talk about weird-looking graphs and weird-looking stuff that you can do with limits. Okay? So we've got a function g of x. That would be this whole thing here. If you look at it, if you remember back from Algebra 2, this is what we call a piecewise function. That is, it's kind of chopped up into pieces, it jumps around a little bit, all sorts of cool stuff like that. And it wants us to estimate the limit as x goes to 3. And as you can see, x goes to 3 is one of those weird points right there. So let's look at it, okay? When you look at it, you notice that there's an open circle, meaning that the point doesn't actually exist there. And then there's a closed circle, meaning that the point actually does exist there. So we get this jump discontinuity here, where we get approximately to here, we get almost to there, and then we jump down, and then we jump back up. And so we got to figure out what it means to do this, right? Like what does the limit tell us about doing this? So again, let me draw something just a tiny bit more zoomed in here. And we'll have 1, 2, 3, and 1, 2, 3, 4. And so, okay. So we've got at 3, 3, we've got that open circle. At 3, 2, we've got the closed circle. And it looks like we're doing like this, jump down, and then continue like that, right? And then this comes down to here. So that's like the zoomed in version, where we're only looking at like that much of it. So the question becomes, first of all, does the limit exist? And the answer to that is, let me again go to a purple color. Am I approaching the same spot both from the left and the right? I am approaching it. And remember, limits are not about getting to something. Limits are about approaching things. Think of a manhole on a street, okay? At the manhole, there's no street, right? The street, there's just a hole there. but the street continues all around that manhole. So at the manhole, there's no street, but as you approach the manhole, there's always street. No matter how you approach the manhole, unless you're actually at the manhole itself, there's still street, right? And that's the same thing here. I approach it. I don't care really that the actual point is there. That is, if they took the circle of concrete that would be the street at that manhole, and they made a mold out of it, and they dropped it down into the manhole, and they said, okay, the street exists down at the bottom of the manhole. You wouldn't care. Nobody's going to drive on that particular piece of road, right? The street exists there, but it doesn't matter. The manhole is what's important, right? And you have to avoid the manhole, and you're just going to do that by driving over it. You're not going to do that by going into the manhole, driving on the little piece of street for a second, coming out of the manhole, and continuing to drive on. So that would be ridiculous, right? So instead, we only care about what we are approaching. We are approaching that manhole. So are we approaching the same thing from both the left and right? Yes, we are. Okay? Then the other part is what is that value? So the limit exists because we are approaching the same thing from both sides. And now, what is that limit? So the limit, whoops, let me do that in blue. So the limit as x approaches 3 of g of x equals the manhole, not the piece of street that they molded and put at the bottom of the manhole. And that value is a y value of 3. So the limit equals 3. Or it appears that the limit equals 3 because you can't really tell, right? Again, when you're looking at graphs, what if that y value is 2.9999999999997? I would never know by looking at that graph, right? It appears that the limit is 3. And that's all I can really say. And that's all you can say for these tables and graphs and things until you get doing this with algebra. And we'll get there. Okay? So I'll give you a moment to look at that. And let's move on to the next problem. All right, another weird-looking thing, right? So, f of x is plotted below another piecewise function, another function that jumps around. And we want to find 3 different limits. And this time, we've got weird things going on. Okay, we've got this little minus there. We've got a plus there. What's going on? We don't really know, right? And then we've got a regular limit here. So let me tell you what's going on here first. This is the limit value as we approach that x value from the left. That is as you start on the negative side and move towards the value. As you start from, if you want to think of it this way, as you start from negative infinity. And then this one is as you approach from the right. That is as you start from positive infinity and move back towards the point. Okay? So, these are called one-sided limits, okay? And so these are called one-sided limits. And these one-sided limits always exist. One-sided limits exist. No matter what, one-sided limits exist. It's the full limit, the limit itself that might not exist if you're approaching from the left and right and you're going to get two different values. Okay? So let's work on this first one. The limit as x approaches -1 from the left. So look at the -1 value. Look at there. Look at what happens. From the left, that is, if we start and approach like that, we're going towards, remember, never getting there, just going towards this one, right? And if we were approaching from the right, we'd be moving like that, and we'd be approaching that one, right? So it looks like the y value as we approach from the left is this, and that y value looks like it is a y value of 1. So approximately, from what we can tell from what it looks like, that limit as we approach from the left is 1. That is, the y value is 1 as we approach that x value. Well, okay, so let's look at b then. Let's approach an x value of 3 right there from the right. So that means coming back like that. Well, that looks like it puts me there. In fact, no matter which direction I go, if I approached from the left, I'd still be approaching that. So, no matter what I do, I'm looking at this y value, which appears to be 2. So, the limit as x approaches 3 from the right of f of x is a y value of 2. Finally, let's talk about the limit as x approaches 1 of f of x. That's right here, and there's all sorts of weird stuff going on here. This would be, so let me try our manhole analogy again. This would be like if we had a street, a real wide street with like a partition thing in the middle of it, and then so here's one side of the street, here's the other side, and here's like the partition thing in the middle, almost like a freeway. And this would be like having a manhole here on this side, a different manhole here on this side, and then somewhere in the middle we said, oh, here's one of those parts of the street that we just decided to put in the median there. That's kind of the idea of what you're looking at there. So then the question becomes, does the limit exist? One-sided limits always exist, but this is a limit, not a one-sided limit. So do we approach the same y value from the left and the right? Well, from the left, we approach that one. From the right, we approach that one. So it should be pretty clear that in this case, the limit does, does not exist. And it is pretty typical notation to use DNE for does not exist. Okay? So I hope that helps with that sort of strange idea there. And that is our last problem for this section. So thank you for listening, and have a wonderful day.